Hello, everyone. Good afternoon. Before we begin, please confirm that you can hear me and see the slides clearly by just typing yes in the chat window. Also, we would like you to introduce yourself, your name, your designation, company, and the country you are based in. It's a pleasure to see an international audience of people from all industries and backgrounds. Good to see you all. We are receiving your messages. Thank you so much for confirming. I would like to thank you all for registering and taking time out on a Sunday to learn about conducting FFS and life extension study for thermal cyclic service piping system. My name is Aisha Khalik and I will be your introductory speaker for today. It's our pleasure to host this webinar for you. This is our 102nd webinar in a series of technical webinars that we are conducting. As a practice, we are conducting one webinar every month. Please follow us on LinkedIn and YouTube and make sure to check our website regularly for the latest update. Today, we have an experienced panel of speakers. I am with my colleague, Mr. Ijazul Karim Rao, who is Managing Director, Principal Integrity and Safety Consultant. Madam Mubina Khatun, she is Director, Engineering Services, and Mr. Tony James William, who is the General Manager, Global Sales at Velosi. Moving forward, during this webinar, we encourage you to keep asking questions to clear any doubts. We would definitely like your engagement on this topic. You can type your queries in the question and answer window and you will receive a reply in the same window, or we will try to answer it live. As we have a detailed question and answer session after the completion of the topic, please accept our apologies if your question is not addressed due to the high number of questions we usually receive. So we have to be selective. Please bear with us. Furthermore, we will also be issuing participation certificates to all those who have attended at least 80% of the webinar and have participated in the discussion through question and answers. So before we begin, although most of us are in the comfort zone of our homes, we should be aware of safety exists. We should keep a safe distance and generally take care of ourselves and people who are around us. Since this is a quite technical subject, we will touch only the key theoretical and practical aspects of conducting FFS and life extension study of thermal cyclic service piping system. In this limited 2 hours, we request you all to follow us along with us and keep asking questions to help us make this session as engaging as possible. So we will be covering Velosi introduction, fitness for service details, standards and regulations for this topic, case study overview, and question and answers. So let us begin, and I will start with Velosi introduction. Velosi is a leading global consultancy firm that provides asset integrity, HSE, engineering, environmental, and software solutions to the client in oil and gas, power, and petrochemical industries around the world. We also have our in-house proprietary software, Whale Plant, which is an industry-leading SAP certified complete asset integrity software suite currently being used by oil and gas and energy giants such as ADNOC, Dragon Oil, TANAP, Emirates Nuclear, BSR, etc. Founded in 1982 in Malaysia, Veloci Group was then acquired by Apple Spain in 2011. We have 43 plus years of experience so far, and our footprints are in more than 86 countries. So far, we have completed more than 1,300 projects with 500 plus multiple clients worldwide. Now, I will request Mr. Ijazul Karim Rao to start with today's topic, that is fitness for service. Thank you.
Assalamu alaikum and good day, everyone. I know that this is as you may know also, this afternoon in Abu Dhabi and late evening in Far East and early morning in Europe and America. So, the today's topic is fitness for service assessment, and it's a big topic and somewhat confusing as well. Why I say it's a little bit confusing? Because general feeling is when we have a API, I'm saying API 579, fitness for service assessment, it means that equipment is fit for service, just like a new equipment, or is a compromising kind of situation. See, API 579 boundary starts when API 510, API 570, API 653 fails. The requirement fails. It means new code requirement fails. Or the metal loss, state metal loss is more than available crane allowance. Then we need to go to the shelter of API 579 to get some more time and to ensure that equipment can be kept in continued service, even though it has certain defect. So this is very, very important. This fitness for service does not guarantee the equipment as a new equipment. It is a FFS with compromising objective. This message has to be kept in mind because industry feels this FFS means equipment is as good as new. No, it's not. Equipment is as good as new. It is a compromised already. and we are getting some extra time. Now I go to the formal discussion of the presentation. There's 168 slides with the case study. So it is a heavily technically dense discussion, and I hope people who are attending this webinar would be benefited. So what is fitness for service assessment? The ability to demonstrate structural integrity of an in-service component containing a damage. This is what I started my discussion. Fitness for service, not for a new equipment, not for a undamaged equipment, because those equipments are as good as new, or within the compliance range of, as I can repeat again, 510, API 510, 570 for piping, and API 653 for storage tanks. You don't need to take shelter under API 579. So ability to demonstrate structural integrity of an in-service component containing damage, this is called FFS. Okay, FFS is to perform, to identify below, component is or has been used, not new. Allow or damage may not meet current design standard. Current integrity is considered. Remaining life is used for guidance on inspections or repair or replacement decision. Now, background. If this process started in 1990, there was a joint industry project in America, and this was the first FFS guideline were prepared. Then in 2000, first edition of API 579 was released. Then in 2007, ASME and API both joined hand and they started working together. Third edition was published in June 2016. And the current edition, which is being used by professionals, was released in year 2021. This is history just. Now, roles of different codes and standards. Like API 579 does not work in isolation. All the applicable design codes, for example, if we take ASME series of standards, ASME division 8, ASME section 8 division 1, 2 and 3, then ASME section 2, ASME section 3, ASME section 4, ASME section 9. Similarly, ASME B31.3, ASME B31.4, ASME B31.4, 8. And similarly, API 650, API 620, tank-wise. So all these standards are playing their role, and accordingly, the relevant standards are selected while making assessment. Then other relevant codes like inspection side or corrosion side, like API 571 for the identification of damage mechanisms, API 570, API 510, API 653 for the inspection and code compliance checks. All these standards are applicable. Similarly, API 576 for the PSVs. So all these standards are required to be used while doing FFS assessment per applicable equipment or component for which those equipments were built. Now, objective, again, fitness for service assessment objective is to get some time so as we can either repair or replace the equipment, or we can continue for a certain period without any action. So why? The objective is this because equipment is found with a defect. Then accordingly, we are doing the assessment. The final outcome of FFS assessment is a decision to run as is, repair, re-rate, alter, or retire the equipment. FFS result can also include an estimate of remnant life, which is useful for planning future inspection in case of continued running and future budgeting in case of equipment retiring. Next, benefit, because we know that like previously, if equipment was not meeting the criteria of, let's say, static equipment, I can say API 510, 570 or 653 criteria should be removed or retired or repaired. But now, since the inception of API 579, we can get some time. So ensuring safety, even though equipment is in defect situation, but we can improve safety and reliability of aging operating equipment, reduce downtime by eliminating unnecessary repairs, better planning of shutdown and replacement of equipment, then improve yield strength if rate of equipment iteration or life consumption can be estimated. Then, like which areas or which kind of expertise are required? It is the multidisciplinary team which should be doing the job for the FFS assessment. For example, corrosion experts are required, corrosion engineers are required. Plant operational experience or operation engineers are required to be involved. Stress analysis means engineering good, thick mechanical design. People who can do stress analysis, who can do finite element analysis are required to be participating. Same like a fracture mechanics. Then metallurgical and material engineering knowledge is also required. Then non-destructive examination experience, NDs, like what kind of techniques are used to do the defective, like a defect assessment or the equipment condition assessment. So just like for the sake of knowledge, like when we're talking about API 579, so this standard consists of 14 parts. Parts 1 is introduction, and last part is fatigue damage. In between, generally, like if you say brittle fracture is a section number like 3, part 3. So practically part 1 and 2 are the introductory parts, and 12 parts are for various kind of damages. For example, brittle fracture, part 3, general metal loss, part 4, localized metal loss, part 5, pitting, part 6. So 4, 5, 6, similar kind of damage mechanism. Brittle fracture mainly is a like UCS 66 or the like a low temperature services check is done by this. Then blister, hick and soic damage, part 7, weld misalignment and shell distortions, part 8, crack lies flaws, part 9, equipment operating in creep range. Interesting, basically chapter 10, and then fire damage, part 11, dents, gouges and dent gouges combinations, part 12, laminations, part 13, and fatigue damage, part 14, which we will be using in today's assessment. Then there are various annexures which provide support to applicable basically parts. I'm not going through this because this is available there. Then if we see the combination, how these parts are combined together is interesting one. Brittle fracture works in combination of part 3 and 9. Corrosion and erosion issues are covered under the combination of part 4, part 5, part 6, and part 7. Then crack-like flaws are basically covered under part 9. Fire damage, this combination of part 11, 4, 5, 8, 9, and 10. Creep damage, part 10. Mechanical damage, part 5, 8, 9, 12, and 13. Fatigue damage, part 14 alone. It also goes with ASME 8, division 2, fatigue and finite element analysis as well. So now there are basically in each chapter, there are 3 level of basically assessment. Level 1, very simple. Level 2, moderate. And level 3, complex advanced, which is done by with the help of like a finite element analysis software. There could be any software, but which can do fracture mechanics and finite element analysis or stress analysis. Whereas simple one is a spreadsheet one, level 1, and level 2 basically is a more than the simple, like moderate, but it is also done via Excel spreadsheet. So now, how we do this? Like first of all, defect is identified, its size is identified. Then we say what is the flaw and what is the cause of this flaw or damage. Then which action, like which technique can be used for this for the assessment of this defect, and then accordingly, what is the applicability of that particular chapter or part, and what are the limitations while doing this assessment. Then what kind of data we need. This is step 3. Then assessment technique and acceptance criteria. Whether we'll be using spreadsheet, whether we will be using software, whether it would be elastic plastic technique or some other or load limit technique. Similarly, step 5 is a remaining life evaluation, which is also part of the study. Remediation action or what recommendation are required to keep the system intact, or what kind of cautions are to be taken by the operating company. Then what kind of in-service requirements, the recommendation is also given, and then the report is prepared, what's called documentation. So total 8 steps are generally taken for any FFS assessment. Then like importance of damage mechanism. This is like we say if some defect is created or seen in the equipment. So we need to understand how this defect was caused. Like what was the damage mechanism behind, and what could be the failure mode next to fail this equipment, and what could be the even consequences. On the same time, for example, if we want to do FFS assessment for any defect, so we need to understand first the current defect growth rate should be either known or should be prevented. Unless and until the damage mechanism will not be kept in control or its growth rate would not be known, so we will not be able to guarantee how long equipment would be kept under operation without having any threat of a failure. So the identification of damage mechanisms, its causes, and its prevention measures should be known to the FFS team. Then they can make proper decision. So it means that like API 579 or API 571 or applicable NACE standards or any other chemical like reference should be kept in hand while doing FFS assessment. Now, there are various kind of damage mechanisms. If you want to have a little bit idea, mechanical, temperature related, corrosion related. What are mechanical related? For example, overload, brittle fracture, ductile tearing, deformation or buckling. Then wear is sliding, fretting, or abrasion related damage, then fatigue is low cycle, high cycle fatigue, thermal mechanical fatigue or erosion is also considered sometime under fatigue. Then temperature mean creep rupture, deformation, microstructural degradation, temper embrittlement, over aging, then oxidation, and so on. Then in corrosion, low temperature corrosion, high temperature corrosion, all are part of these corrosion issues. Like if you see brittle fracture, no deformation, but equipment could be broken because of lack of toughness due to low temperature. This is like Joule-Thomson impact when temperature goes down and equipment may lose its ductility. Then ductile failure, always deformation. Ductile, when ductility is not lost or hardness is not lost due to the basically low temperature toughness loss. Now, brittle like a cleavage or ductile like a dimples which can be seen in the microstructure of the material. So this is an example of the brittle fracture where due to low temperature equipment was failed. Then creep failure, which is basically high temperature runs. If equipment, for example, there could be a fired heater or reactors tubes. If they are exposed to excessive temperature variations more than their limits, then they can also fail due to creep failure due to high temperature cycles. Then initiation of fatigue crack, like generally it create like due to this is mechanical fatigue due to thermal cycles or vibrational cycles. Then metal loss, which is normal corrosion and which can be seen by naked eye or it can be measured by UT. And then based on the metal loss recurring rate aspects, assessment can be done. So this is metal loss from pitting. Like if localized pitting is there, internal or external, which can also be assessed. Then there's a one important aspect which is covered under basically FFS assessment level 1 and level 2, which is called RSF. RSF is remaining strength factor, which is LDC over LUC. LDC is limit load of the damaged equipment. LUC is limit load of the undamaged equipment. So like RSF, if it's greater than 0.9, equipment can be considered fit. If it is less than 0.9, then it is considered not fit or equipment has to be re-rated. So then like application point of view, like on which kind of equipment, geometrical shape, FFS 579 can be used. It can be used on cylindrical, spherical, formed heads, pipe bends, and like usually classified as a primary equipment. These are equipment type A components. Then type B components like nozzles, piping systems, reinforced zones of the conical transitions like integral tube sheet connections, flanges, cylinders to flathead junctions, usually classified as secondary components. Then component C, like here, these components do not have a design equation that require which pressure equation can be used, and thickness could be calculated, nor these code design can be applied. For example, pressure vessel head to shell junctions, stiffening ring attached to the shell, skirt and lug type supports on the pressure vessel, tank shell cores to tank bottom junctions. So here we have to use some other empirical equation for the FFS aspects. So we have to keep this in mind. So this APA 579 is being applied only on the pressure containing part. Non-pressure containing parts like structures, the APA 579 is considered not applicable. Then applicability and limitation of level 1 and level 2 procedures. Like here, the original design criteria was in accordance with the recognized code or standard. The region of metal loss has relatively smooth contours without notches and is away from structural discontinuities. What is structural discontinuity? From any particular nozzle, from any major T-joint, or where structural continuity comes. So this defect should be away. 579, if there is a structural continuity near or cyclic service, or there are secondary stresses coming on the equipment, then level 1 and level 2 normally cannot be applied. So then the region which it should be away from the structural discontinuity, the component is not risk from the brittle fracture, APA 579 part 3 check can be done. The component does not operate in the creep range of the temperature, then component is also not in the cyclic service. These are the limitations with level 1, level 2 does not work. Then like level 1 normally type A component, internal pressure with negligible supplementary loads. Then level 2 assessment, typical A and B component, internal pressure and supplementary loads. And type A, B, C components, all it can be covered under level 3 and all kind of conditions because it is finite element analysis based working or the lot of calculations are done based on the applicable empirical equations. So now what kind of data normally we need? So original equipment design, it is like a data sheet, it is design calculations we need. Then equipment inspection and maintenance history. We also need, like, if the defect is there, what is the size, their dimensions we need to use. And then if there has been any kind of risk like RBI done, or we have the previous corrosion study or RCA report results. So those all can be used as a good inspection, like good reference data for the assessment of the FFS. Like here, if you see, this is the one defect where the metal loss shown outside. So the grid is shown: pressure vessel shell, inspection grid, metal loss. So here in all these boxes is not equally metal loss. Maybe in the middle there is a highest metal loss. In the edge there could be less than metal loss. So that's why this equipment is divided into these like cells, and each cell is basically given the thickness, which is average thickness of that part, keeping the worst metal loss there. And then accordingly, there's a spacing, and accordingly assessment is done based on these calculations. This could be another like inspection data, point thickness readings. Like here is no grid. Previous one there's a grid. If you see, previously there is a grid. Now there is no grid, only point metal loss. So then this can also be assessed. For example, thickness measurement, metal loss. This method should be applied if metal loss is general minimum of 15 readings required. Coefficient of variation like it could be less than 10%. Then here, COV gives a measure of scatter in data as a percentage. Equation to compute given in table 4.3 in the standard, and it can range from 5% to 15%. So RSF equation, for example, level 1 and level 2 calculation, if FCA like the is basically applicable for the type A equipment, and then level 2 also, the ratio wise, if you see, level 1 assessment acceptance criteria and level 2 assessment acceptance criteria, little more calculations, but result wise it can give you the comparison. Like RSF, in both cases, it should be less than 0.9. Average measured thickness from the critical thickness profile, average measured thickness from the point thickness reading, it both can be used. But both sides, like there should be some FCA, should be available. Like a T required, T measured minus FCA should be greater than or equal to T minimum. Right, sir? T measured minus FCA should be greater than or equal to T required. The equation is same. Like whatever the minimum measured thickness is there at the defect location, that should be greater than the T minimum required by the calculations. And minus FCA. FCA mean future corrosion allowance. For example, if there could be still an active damage mechanism, some metal loss would be taking place. So how much time would be available for that particular metal loss or corrosion rate? So then there are various softwares which can be used. We are not promoting any. You can use any. So Excel spreadsheet for level 1 and 2 are good enough, but we have used also PV Elite is there that can help you to do the calculation. Signal FFS software is also there, and COED compress software is also there. These are the level 1 and 2. Level 3, there is a ANSYS, or there could be other softwares can be used. So this is like a spreadsheet. I'm just showing we have a spreadsheet, all the calculation for this is like level 1, right? And then it could also go to level 2, but I cannot go all these like component, but Excel spreadsheet is available and we have been using it. So this is the second continuation under level 2. So I'm not going through these details because it is like can take on the more detailed calculations, but we are giving just concept. These Excel spreadsheets are available and developed by various engineering houses. We have also developed overs we can use. Right now, just to check, we have spent some time, okay, so to see if you are active, people are not sleeping or getting bored. So what is the primary purpose of fitness for service? So gentlemen, write your answers in the question answer window. So as we understand, I am taking you along. So what is the primary purpose of fitness for service? To determine the cost of the new equipment, to schedule routine maintenance activities only, to decide whether damaged or flawed equipment can continue to operate safely, to design new equipment according to process requirement. So the mostly results are right. So the answer is B. So just to keep you a little bit active. Now standards and regulations like API 579 is one standard, but other standards which are relevant, I mentioned earlier also, like ASME 8, Division 123, ASME B31.3, API 571, API 570, API 581, API 510, API 653, and others also. Like we didn't cover all, but some important ones are referred here. which are used as a supporting standards. Like this one is just, if you see ASME 8 ASME section 8 division 2, but I'm showing 2015, but it could be latest standard. My slide is older, so I apologize for that. So there could be new standard. So this is another slide, like a different content list of the ASME 8 division 2 standard is shown here, not one. The big title. Then API, sorry, ASME B31.3 content list is for piping systems. Then API 570, this is for piping inspection code, in-service inspection, rating, re-rating, rating, repair, and the alteration or of the piping systems. Then damage mechanism affecting fixed equipment in the refinery industry, API 571. Risk-based inspection, both API 580, 581 index. Then like API 510 is for pressure vessel inspection, in-service inspection, re-rating, repair, and alterations. Then tank inspection, repair, alteration, and reconstruction is API RP 653. So question, just to check, like if we have some idea about these standards, which code is used for inspection, guideline, and code compliance checking of the piping systems? So the answer options are: A is API 570, B is API 579, C is API 510, and D is API 653. Answers are coming like mostly right. It is A, API 570 for the piping inspection and inspection related guidelines. So now we have completed almost half of the part where introduction of FFS, its techniques, approach, and what we achieve. Now I will be proceeding towards the basically the case study. Question answer session, which would be live question answers, will give you also chance to ask these questions live by speaking into the Zoom. So that would be the last stage. So now I start with the FFS case study. This case study, what we are presenting today, it is more complex one, and this FFS study is done by using Caesar 2 software and stress analysis software and fatigue analysis software. So it is sometime like a special, like a thinking how we can use that. And let me go through the part. Like to perform stress analysis by using Caesar 2, determine the cyclic load of piping components. The code compliance of piping under its original design condition is checked, including stress levels and flexibility requirements. Then to perform FFS assessment as per API 579 in order to check the operational safety and integrity of plant 3. For example, system 1 and system 2 and plant line system 3 and system 4, piping up to year 2038 by using Caesar 2 output loads and data from latest NDT reports. To determine that operation can be continued safely or any repair replacement of piping is required as a result of FFS assessment as per API 579 section like 571 or ASME FFS 1 standard. Now scope, carry out, because I have to just get you along. Then there would be some fast slides. Here I have to spend little time. The carry out FFS and Relive assessment as per API 579 guidelines for all carbon steel piping subject to thermal cyclic fatigue. The review of inspection history of piping tags for verification and validation of FFS assessment, API 570 basically. Then prepare a detailed working methodology as how the various stages of FFS and remnant life assessment have to be planned for each piping system. Identify critical location of the piping that require advanced NDT checking. Then, if FFS and remnant life assessment requires piping replacement, merit demerits of the local repair also to be mentioned in the report. Preparation and submission of FFS remnant life assessment reports to LNG plant for a review and components. For review and comments basically. Final report preparation after incorporating the components and submission along with a final presentation to the basically client. Issue repair and recommendation report for piping that have been assessed and identified by FFS as not fit for service up to 2038 for LNG plant review and approval. So here, the client awarded project to Velosi to perform FFS for plant 3. So data is changed. I would like to clarify. The names are changed. Some information is mixed between two clients. So as this information does not reflect any actual situation of any client. So that is a claimer from our side. We are not exposing real data for the client, for our client basically. Here, the client awarded to Velosi to perform FFS for plant 3 and 9 thermal fatigue piping system based on inspection and maintenance history. The FFS study of 41 piping tags of plant 3, dehydration and mercury removal unit is done, and breakdown of these lines is given as under. Total 41 lines, system 1, 9, 9, 18, and system 2, 12, 11, and 23 deliverables. So we were required to deliver FFS assessment report for feed gas inlet and outlet piping system of the gas treatment unit. FFS assessment report for raw liquid inlet and outlet piping system of the LPG treatment unit. Then detailed deliverables, collection and review of the engineering, operating and historical records, identification of applicable damage mechanisms, marking of isometric for execution of field entity inspections, and field inspections are also supervised. Then remnant life assessment in accordance with API 570 requirement, identification of peak stress locations, failure point by performing stress analysis, then fitness for service assessment by fatigue analysis using same Caesar 2 software. So this is the technique, the same step which we explained. So here, if I try to show you data collection, then review of the data, inspection history, field verification, then stress analysis, then fatigue analysis. So by all this calculation, we reach to the final FFS results. The same steps which we show in the flow chart, the collection and review of the engineering, operating and historical records, marking of isometric for execution of field entity inspection and execution of the field inspections, remnant life assessment in accordance with API 570. Some repetition is coming in my presentation. Sorry for it. But fitness for service assessment level 3, for example, identification of applicable damage mechanisms, identification of peak stress locations, failure points by performing stress analysis. Then it is done, basically not pending. So stress analysis for as-built condition or as a new plant, then stress analysis for 25-year design life with 11,863 cycles, stress analysis for 29 years design life, 13,000 cycles, then stress analysis for 49 years design life with 22,000 cycles. Calculation number of cycles are also done based on the operation mechanism or scenario of the particular plant. Then assessment of remnant fatigue life as per API 579, preparation of finding and recommendation. So these are the basically steps. Basic data required, the same what we collected: PFDs, P&IDs, isometrics, historical data, plant operating data, entity data. Then we also collected their previously RBI assessment results with the identified corrosion loops. Then, what was the process basically? It is LPG going through to remove water, adsorption process, and after a certain period, the system require regeneration because the adsorption kettle, a bed, may be already reached to a point where it cannot adsorb more water. So then at that stage, the process shifted to train 2 or the equipment B, adsorption tower B. And under that process, this first adsorption tower will go under depressurization, and then we have to regenerate the catalyst bed to be more active, and then after regeneration, which is high temperature, then we have to repressurize the system again. So in this way, the system go to the cycles, and this cycle was being completed almost in 11 hours. Adsorption process is there, where the adsorption taking place between 20 to 30 degrees Celsius. Then depressurization also takes place between 10 to 20 degrees Celsius because the temperature drop when depressurization take place. Then the regeneration, which is high temperature gases are passed through the activation bed to activate the bed 270 to 435 degrees Celsius. And then regeneration cooling is done to the 2030. So it means that a lot of variation of temperature, which is causing a lot of thermal expansion and contraction in the piping system, which cause these cyclic loads on the piping systems. Then repressurization means system goes again to the operation. So here, one complete cycle, not 12 hours, 18 hours. Therefore, 1.3 fatigue cycles are completed in single day, and total of 13,760 cycles are considered for the last 29 years of the operations. Here, inspection history finding, so the facilities were installed in 1990. Then we got the inspection data, like a visual inspection, UT, DPT, thermography, PRT, all kind of inspection results are taken, collected, reviewed, and the kind of defects which were there also, for example, heavy pitting, metal loss from CUI, coating, deterioration, external corrosion, validation fatigue cracks, vibration fatigue cracks, are also could be also be one of the troublemakers. Here, repair replacement 16 piping tags since 1990 who are basically either repaired or replaced. Then full replacement 7 lines from 2009 2013. Then sectional branch replacement 9 lines 2011 and 2013 and 2017. So all this history was reviewed. Then visual inspection results, like what kind of troubles are there. CUI related lot of issues were seen, and then there were certain issues on the piping supports because of high thermal movements, and those were also being kept in good shape, but there were indications some problems were caused by the thermal movements of the piping system on the piping support side as well. Since there's a high temperature to low temperature cyclic service, CUI is a problem, and then somewhere the caging was also done to remove the CUI problems. Here, like the thickness, measurement records, we found that for 10 lines there was no metal loss, but 26 lines shows metal loss ranging from 0.01 to 2.37 mm, basically from like 0.26 to 27.8% metal loss. Then remedy life, we have followed the basically the mechanism of API 570. Here, like we start with the metal loss, then what is the remaining corrosion allowance, and then what is the measured corrosion rate, short term, long term. Then accordingly, RLA is calculated. Then here, like corrosion rate calculation wise, inspection, review, metal loss, then is short term corrosion rate or long term corrosion rate. We also compare it with the expert corrosion rate, estimated corrosion rate, and then design corrosion rate. So 4, 5, like if I can may say again, design corrosion rate, estimated corrosion rate, expert corrosion rate, or measured corrosion rate. So these 5 corrosion rates are compared with, and then accordingly, short-term, long-term basis, we see what is the worst corrosion rate can be used. But preferable corrosion rates are the measured corrosion rate based on the long-term and short-term both comparisons. Then corrosion rate measurement, long-term corrosion rate is there, short-term corrosion rate is there, and the formula-wise, if you see that measured corrosion rates, like second last inspection and minus T measured, then date and date of the the time period during that. So accordingly, the same formula, like whether we are taking 2 inspections or we are taking an interval from the last inspection to the startup, that could be a long term, and the metal loss between 2 inspections and the duration between 2 inspections, that is called the basically short-term corrosion rate. Then how we calculate the remnant life, the T measured minus T required divided by measured corrosion rate. Then accordingly we can see what is the remnant life of the equipment. So here the results are shown, all calculations are not shown. Most of the piping system, like if you say nominal thickness, minimum required thickness, minimum measured thickness, metal loss, corrosion rate, and then accordingly remnant life. The remnant life was all piping system was greater than 25 on the linear rate basis. So here we are not talking about cyclic service, but we're talking about metal loss related remnant life, not thermal cyclic related remnant life. So it was found within acceptable range, because wherever defects were, those pipes were already replaced or repaired by the client. Now, before I go again, question to keep you alert or involved. What is measured corrosion rate? Check, sir. Wake up, all gentlemen or ladies. Wake up. And what is the question? Like how you answer? What is measured corrosion rate? The option is the corrosion rate which is calculated with the help of empirical equation. B, the rate of which metal react with oxygen in the presence of heat, calculated as corrosion rate is equal to exposure time and weight of sample. Or the rate at which metal thickness is lost over a time, typically calculated from the thickness measurements. Corrosion rate is equal to delta T over delta T, like net metal loss divided by time. And D is the rate of metal production during refining, calculated from chemical recovery. The answer is mostly correct, all correct. Item answer is C. So these questions are being added so as I can get you involved, because we are not asking questions in between. So at least you can see like yourself involved, like what is being presented. Now FFS approach for like where we are saying it is a level 3 assessment. We have done APA 570 assessment where equipment is fit for 25 years, but we don't know if the thermal cycles wise we can continue these piping system because they already completed their design life. So here the approach adopted for evaluation of these assets allows the 8-step methodology defined in APA 579 level 3. We already discussed earlier, flaw and damage mechanism identification, then applicability and limitation of the fitness for service assessment procedure, data requirement, assessment technique, acceptance criteria and results, remaining life evaluation, remediation like covered under recommendations, in service monitoring recommendations, covered in recommendations, then documentations also. So here, first we check minimum required thickness as may be 31.3, which is already done. Piping elements loads are derived from Caesar 2 piping stress analysis. Then piping stress, like if I can make a little bigger, this is like a 5-step under assessment technique and acceptance criteria. Very important to keep in mind. Like piping stress analysis for piping elements using corroded wall thickness is performed. Also, the stress analysis is done as a new piping. Then the stress range is calculated from the piping elements loaded obtained from the Caesar 2. Then fatigue life is calculated from the component with corroded thickness as per EPA 579 part 14. So now we have done two cases basically. Assessment of fatigue damage life as per EPA 579 part 14 with nominal thickness, no metal loss. Okay, sir. Like, but operational life is considered in the objective. Then assessment of fatigue damage life with minimum measured thickness as per the as found condition of the piping system. Then step 2, damage mechanism identification. Here, the main damage mechanism is thermal fatigue. The result from repeated temperature cycling, loading to cracking due to thermal stress, because this thermal fatigue can cause any crack in the piping system and which will lead to a failure. Then other damage mechanism which could be assessed, but we assessed under APA 570, that was CUI, then atmospheric corrosion as well. So these two damage mechanisms were taken care by the client, and wherever there was a defect, the pipes has been repaired or replaced. But this damage mechanism, which is like unseen and only, but no evidence seen on the like piping as a crack, but this has to be assessed. But like how much cyclic life is left for this piping system, whether client would be able to operate this piping system up to year 2038. Remember, this plant was installed in 1990. So it means we are talking about almost 60 years operating life. No, 90 means, yeah, almost 50 years operating life. So application point of view, if we see that, we are taking API 579 part 14 level 3 assessment, method C under cyclic operating conditions that would be used. The level 3 assessment procedure is consistent with modern fatigue analysis method employed in numerical fatigue evaluation and durability software application designed to post-process result directly from a finite element analysis. The fitness for service assessment procedure for evaluating fatigue life component subject to cyclic service below the creep range that do not contain crack-like flaws. This is the application. Geometry complex component subject to complicated transit loading from pressure and thermal effects, where the post processing of results from a finite element analysis can be desired. Component subject to non-proportional loading. The component is subject to loading where the sequence of loads may have an effect on the fatigue life. The component may contain volumetric flaws such as thinning, pitting damage, and weld misalignment. Limitation: the assessment process procedure only apply to components that are not operating in the creep range. The component may contain volumetric damage from general thinning, local thinning, pitting, or weld. The component does not contain a crack-like flaw. The component does not contain stepwise cracking or sewing damage. So this is very important when we're doing this assessment. So like a data requirement, what we collected, PFDs, P&IDs, asymmetric drawing, inspection history data, right? And then process description, piping class and related data, inspection history data is also next stage. This is important to collect. Here, step 4, assessment technique and acceptance criteria. Here we have used, like AB57 considered overall integrity of the assessment, like we have used the overall integrity of the piping is assessed using Caesar 2 software, is a hexagon, and Excel spreadsheets also used. Fatigue damage assessment is performed in accordance with APA 579 part 14 level 3 method C. Assessment is based on accumulated damage over the intended life of the equipment. In the current study, total life is considered from installation of 1990 until the current expected retiring target of 2038. The results in like 22,776 cumulative duty cycles. For a successful assessment, the cumulative damage for an entire number of duty cycles should be less than 1 basically. Next, the remaining life calculated based on the formulas where we have to accumulate the result. Now, under Caesar 2, how we do that? Assessment of a system via Caesar 2, input parameter in Caesar 2, load cases, operating cycles, stress analysis result, and then fatigue analysis result. Now, we are going into the Caesar 2 criteria. Here, like if you see, since we are not presenting Caesar 2 as a demonstration, but this is a like an input screen, which is also modified. We have an input screen, and then this is the model where the complete piping system is modeled on the as per actual isometrics and support locations, all with the connected nozzles and anchor or the guide locations as well. Then this is also a little bigger. The previous one showing more data, and here on right side you can see a more like a practical show of the piping network. So here, if you see assessment of, we're taking the various systems are there. We are showing you only one piping system. System one overview include piping 18 piping tags, 9 per contract and 9 additional for the stress boundary completeness we did. Then system one boundaries mean piping from feed gas dryer, tags also changed, bottom nozzles to mercury removal, after filter like a 3T this unit. Then piping from regeneration gas heater to feed gas dryer and bottom nozzles. These are like a boundary limit for the piping system one. The data what we use, like the diameters of the pipe, like there are like a 1.4 to 1.5 inch, 2 inch to 10 inch, 12 inch to 24 inch, and 26 inch to 30 inch, and their respective thicknesses. And this is the material of construction. Then this is the crane allowance. This is the piping class, piping material, nominal diameters, pipe schedule which is used, and the crane allowance also. So this is the data which is used as an input to the Caesar 2 along with the operating and design conditions. So while model is completed, we run various cases. So we are showing you how the various load combinations are used to run the analysis in the Caesar 2. Total 125 load cases were developed and analyzed, but we are showing you only few cases as a sample. Load case developed for the modeling. Then like operating cycles, what we basically considered, like that is like how much time, how we calculated the time for the total cycle completion for this drying process. The molecular sieve gas desulfurization unit consists of 3 adsorber tags are there, 2 in parallel adsorption and 1 in regeneration. The unit operate on a 12 hours adsorption cycle, 6 plus 6 hours. Then 6 temperature and pressure are considered to reflect different conditions of adsorption and regeneration between feed gas dryer ABC. The adsorption and regeneration process of the feed gas dryer are illustrated in the like a slide next. For example, the 4 stress analysis files were evaluated for different operating lifespans. Stress analysis for as-built condition, then stress analysis for 25-year design life, then stress analysis for 29 years design life, and stress analysis for 49 years design life, where different number of cycles are identified. So this is the like a one case of the dryer. If you can see that, like the components are shown, the components are connected. This is another case. See, these things like cannot be taught, but we are giving you awareness how we model it and how the physically look like, so you can get the idea. Next component, like a screen. And now stress analysis results. Now we are showing you where the maximum stress was resulted or reported by basically Caesar 2. See, this is the case, what we are showing you, assessment of the piping like a fatigue life with nominal thickness and no metal loss. This is as new. Now, next would be like stress, like node number 7010 or 1650. Here, stress ratio is 98.7 or 89.5%, right? So the sample collection piping tag is showing highest stress. Process hydrocarbon piping tag is showing highest stress. So these are the locations where stress was reported on the higher side. So if you see that, this is the piping along with the big pipe, there was a small pipe, right? Where small pipe, this area was under high stress, and you can see that also if a small bore connection is connected with a big pipe, that could be subject to like under fatigue stress and it may fail. This was shown. Similarly, other area, this is sport location where high stress position is shown by Caesar 2. So if you see that, since we are doing stress ratio first, interestingly, 25 years, 29 years, and 48, everywhere allowable stress ratio remain more or less same, like 28% here, 28, 28. So there's no stress increase in stress analysis. But in fatigue analysis, you will see there would be another kind of scenario. So the first thing is stress analysis by Caesar 2, which shows the stress ratio and high stress points can be seen, and then focus can be given to those points. And those points may become a weak point or at some stage may fail. So under fatigue analysis, then we went live wise. So fatigue analysis, 9 fatigue load cases considered, 1 complete cycle 18 hours, 1.3 cycle a day, total number of cycles for 29 years 13,760. So here remaining cycles were left till 2038, and also other case the remaining cycles are still balanced. For example, for this piping system, stress ratio 89.5%, partially replaced in 2017, turnaround, and remaining cycle calculated till 2038, save for continued operations. Monitoring annual vibration and crack initiation and thickness checks as per API plan. So this was the recommendation. Remember, the metal loss wise, these pipes are already safe. Now we have checked as per the number of cycles, and this number of cycles assessment and fatigue analysis both are also showing the piping is safe to keep in service till 2038 as per the target of the client. So now if you see that, like now case 2 we are starting, where 2 piping system we're taking as a sample, and here we will be analyzing these piping system as per their minimum measured thicknesses, right? Previous one is done as per the nominal thickness. Now we are doing as per the minimum measured thickness. So the steps again: minimum wall thickness for internal pressure, calculated for ASME B31.3, Appendix 2, and adequacy confirmed. Then piping load obtained from Caesar 2 stress analysis. Then stress analysis performed using corroded wall thickness. Stress ranges derived from Caesar and applicable loads. Fatigue life calculated for corroded component as per API 579 part 14. So this is the basis of the history, where we have taken the history of this piping tag. During piping stress analysis, high stress is found at node 7010 with the piping tag number this as shown in figure 8.7. According to inspection report of year 2021, the minimum measured thickness is 3.82 mm at node 7010, and its nominal thickness is 3.91. Some metal loss was there. The full length replacement of this line has been done in the year 2009. So we have considered corrosion rate of 0.005 mm per year based on the long-term corrosion rate, and the same corrosion rate has been used in thermal fatigue assessment. Similarly, other piping tag, similar history. We have taken the corrosion rate of 0.02 mm per year. Now, the calculation of the minimum required thickness is done as per T is equal to PD over 2 SCW plus PY, and this is like ASME 31.3 formula. So here, the remaining corrosion allowance available still exceed the original corrosion allowance of 1.6 mm. Based on the result obtained from thickness calculations, it is concluded that the measured wall thickness is still more than the required wall thickness. Calculation cover hoop stress under internal pressure. Adequacy for thermal cyclic loading is addressed in the next section. Here, if you see that, now we are going to thermal expansion stresses for corroded piping component. So element forces, piping sectional properties, like calculated using corroded wall thickness, stresses, axial bending, torsional calculated for ASME B 31.3 clause 319.4.4. Then stress intensification factor SIF applied for elbows and T's for ASME 31.3 Appendix D and B31J. Here, the piping tag considered for FFS assessment again, we continued. Now, node 7010 piping tag. See, so what we checked here, forces and moments for the worst load case taken from Caesar 2, piping sectional properties calculated using corroded wall thickness, code stresses of the corroded component are within allowable limit except the node 605 and 7010. Maximum stress ratio at node 7010 observed. Stresses calculated using current thickness minus design corrosion allowance. Remaining fatigue life sufficient for continued operation till 2038. Conclusion, piping tag is fit for service until 2038. based on stress and internal fatigue analysis. This is the result basically. Now, if we see here, like the table load of piping elements, node 7010, piping tag number this, you can see the various loads, like where SIF, for example, plan 2.52, and the shift plan ratio wise shows more or less same, and these are the moments and the basically forces. Now node 1650, piping tag number this, forces and moments for the worst load case taken from Caesar 2, piping sectional properties calculated using corroded wall thickness, then code stresses within allowable limits except at node 1650, maximum stress ratio at node 1650. Then stress is calculated using current thickness minus design corrosion allowance, remaining fatigue life sufficient for the continued operation till 2038. Conclusion, piping tag is fit for service till 2038. Now, the same tag, there is a basically SIF ratio, or the movement and the forces which would be used for the equipment nozzle design and its subsequent impacts. Calculated stresses for corroded pipe, like if you see that the ratio wise, the 38.36 is quite low, but one area the ratio is exceeding, like 111.21% for node 1650, and also 99.51, the same area, different combinations are there. So here, like since we have told this has to be either monitored and some corrective action has to be taken for this particular node. Now, question for you to get involved. I know that like if we don't ask questions, some people may sleep, right? So the question is, FFS assessment in this case study is done in accordance with API 579 part number. Very simple question. Whether it is done as per part 4, whether it is done as per part 14, whether it is done as per part 9, or whether it is done as per part 412. The answer is coming, yes, mostly right. It is as per part 14. Thanks for the correct answer. Now, fatigue life assessment of corroded piping elements and remaining life calculations. Like what we saw, the based on, like, see now, because most of the work is done by Caesar 2, and we made the model, we put the condition, we made the load cases, the rest results are being presented. So that is becoming like some gray area in between, because there's a Caesar 2 software, and that is doing this fatigue analysis. So that one cannot be like demonstrated because calculations are all behind the scenes. So fatigue life assessment for the corroded piping element and remaining life calculations. Based on displacement stress calculated in the previous section, the fatigue life of the corroded component is calculated for API 579. The material fatigue curves are taken from API 57 and Exercise 14b, which are the same as mentioned as in section 8 division 2, like fatigue life assessment for corroded piping elements, then piping tags both like a 03PS44 and 03PS019. Next slide wise, if you see this, based on the displacement stresses, the calculated in the previous section, the fatigue life of the corroded pipe corroded component is calculated as per 579 division 2. These are the basically two tags. Maybe some repeated slide here. So now here, like number of cycles, this is where we are saying how many cycles this piping tag can sustain. That is basically the key result assessment. So here you can see this piping system can withhold infinite number of cycles. But this piping tag here, 40,000 cycles. This one, 67,000 cycles. So these number of cycles, basically we know that how many number of cycles are required, 13,739 here. From below table, it is seen that the most of the assessment nodes still have fatigue life. However, per node 7010, thermal fatigue is a controlling factor and is fully corroded condition. 13739 thermal cycles are allowed. This one, right? 13739. All other places, number of cycles are more, right? So this is basically a calculation result. The fatigue life assessment result for corroded piping element node 605, piping tag number, this is a limiting component. So similarly here, if you see, the most assessment nodes still have long fatigue life, and the thermal fatigue life for the node 1650, right? This is the limiting site, right? The fatigue life assessment result of corroded pipe element number, this here 36,000. Yeah, 36,000 is the lowest number coming there. So now we are reaching toward the conclusion of our presentation. like a fatigue life assessment for corroded piping element remaining life calculation. If I read it, because it's a result, the fatigue life is an accumulative damage. The fatigue life calculated for piping tags for a virgin material with corroded thickness since the piping of interest was put in service since 1990 and it has been in service for 29 years. The accumulated cycle or 13,760, assuming 29 years of continuous operational life and 1.3 cycle per day. To calculate the damage for these cycles, assuming one fatigue damage accumulation with different stress ranges by using minor rule and with calculated corrosion rate keeping constant throughout the service, then the damage in the past operation can be calculated. The calculations are shown like this equation. Now, however, the thermal stress range increase as wall thickness become thin. If it is further assumed that the corrosion is controlled by applying proper painting and protection, then the remaining life of the component can be considered as per this equation, number of cycle equation. So here, if you see the fatigue life assessment for corroded piping element and remaining life calculation for piping tag number this, like according to the inspection report year 2021, the minimum measured thickness is 3.82 mm at node number this and nominal thickness is this. The full length replacement of this done in that period. Now, the line is fit for service till year 2023. However, it should be noted that these cycles are calculated based on the current corrosion rate. If the corrosion rate increased, then the additional assessment would be required. Here, this is the fatigue life, if you can see number of cycles which are calculated for this piping tag by Caesar 2. So this is the next tag calculations. The similar results are presented. And this is also, you can see the number of cycle and fatigue life for tag number 2. So this is node number 2. If you see that, like all code stresses of the corroded component calculated within the code allowable stress except at node 605 and 7010. The maximum stress ratio appears at the node 710. These stresses are calculated based on the current measured thickness minus design corrosion allowance. The number of remaining fatigue years for the piping tag are still enough for the continuous service till year 2038. Therefore, based on piping stress analysis and thermal fatigue calculation, this piping tag is fit for service till year 2038. So similar presentation for the other tag. And here if you see that all these piping tags where the life is like a design case, fatigue case, the results all acceptable till 2038. So conclusion recommendation is the last part. Like the piping shows the highest stress 98.7% but was replaced in year 2009 and is safe for operation till 2038 based on the remaining cycle analysis. Annual monitoring for vibration, crack initiation and thickness reduction is recommended as per the RBI plan. Then the piping shows high stress other one. This is the tag number 0019, 89.5% but was partially replaced during year 2017 turnaround and is safe for operation until 2038. The same kind of recommendation is there. In piping, the piping is overstressed like one tag which at the node 460. However, due to minimum thickness loss and 3.5 safety factor, it can operate safely until 2038 and the routing is inflexible and cause high stresses. Yearly monitoring for vibration, cracking, and thickness reduction is required with immediate replacement if metal loss exceed the design limit. So these are the areas where recommendation is there, where some modification is required, some problem is there. So this is the location shown, like a resetting support removed from the line number this, resetting support removed from the pipe number this, so as to get some more flexibility. This is the modified resting support with 0.1 friction factor and resting plus Y support removed from the line to show some flexibility. So the final recommendations, it is recommended to apply corrosion preventive coating to areas where CUI is observed for the piping. For the inlet piping, a regular piping inspection program as per EP 570 is sufficient for the future maintenance, provided that the prevention of the future CUI is addressed. Then piping tags referred with high stress should be monitored closely. If any crack-like flaws appearing, the consideration could be given if replacement of these pipe tag could be made with better flexible design and modified supports. The remaining wall thickness of the pipes and associated remaining corrosion allowance are the key factors in the assessment of the future fatigue life. Therefore, future monitoring, thickness monitoring, and vibration monitoring of the overstressed pipes are mentioned to be followed. It is also recommended if thorough inspection could be performed in next shutdown, as it will ensure actual condition of the piping systems. So it concludes the presentation. Now we have two questions which you people would be asked to answer, and then we will go for open question answer session. So here, which software is used for fatigue analysis of this piping system, what we discussed? Just to make sure, like you are familiar at least the what software we used. We are not promoting Hexagon, but the software what we use, which you people can remember. Option A, PV Elite, pressure vessel software. B, whale plant, asset entity management software. C, Excel spreadsheet. Or D is Caesar 2, design stress analysis software, piping stress analysis software. Answer coming, all correct. It's D, Caesar 2, basically, Hexagon Caesar 2 piping stress analysis software for fatigue analysis. Now, one more question, which is the last one. How many parts are there in API 579, including introduction? So, answer coming for this question, like how many parts are there in API 579? At least we should remember that now. We studied in the beginning. Answer coming? Yes, answer is C, 14. So we completed our discussion. Now we'll take some live questions. We hope that this session was useful and you have obtained some knowledge about API 579, some knowledge about like a cyclic service, and how we can do like a finite element analysis or Caesar 2 analysis for thermal fatigue piping systems.
We are seeing some participants raising their hands, but we have already received some questions in the Q&A panel, so we'll be going with them first. So we will start with Mr. Dawood Ali Nadaf. Mr. Dawood Ali, we have allowed you to talk. Please unmute your mic and ask your question. I think, Mr. Dawood Ali, your mic is not properly working. So anyway, we will...
You can read the question. Like if multiple damages are identified like a metal loss and crack, then FFS is considered and performed in a separate calculation. That's one question. What are the criteria to decide whether it is a short or long-term corrosion rate? These are the two questions. So see, here if you see, we have assessed multiple damage mechanisms. There are three damage mechanisms, what we assessed in this particular case. One is fatigue, thermal fatigue due to thermal cycles. Second was CUI, corrosion under insulation. And third was also general corrosion. So it means that like we can assess 3 or 4 damage mechanisms in one go if they are causing the similar kind of issue. Here we are using API 570 calculation first, then maybe we have to go for part 4 and 5 if applicable, or we have to go straight away to level 3 assessment. So the assessment is done considering all the applicable threats or damage mechanism which cause that particular defect. And then we assess the defect by applying FFS approach as given in API 579 applicable parts. And number 2 part, the question was whether we use short term or long term. Like we try to compare both short term and long term, and whichever is conservative or more corrosion rate, we use that particular corrosion rate. Whether it's short term or long term, we try to follow the more higher value corrosion rate.
Okay, thank you, Mr. Dawood Ali. Now we will move to Mr. Kamal Braham Chouch. So, Mr. Kamal, we have allowed you to talk. Please unmute your mic and ask your question.
So, question was, when you see, okay, the question is, what is the difference between FFS level 1 and level 2? Basically, there was a detailed like a discussion in the beginning. There are 3 levels of FFS, whether level 1, level 2, and level 3. Level 1 is like a basic, and level 2 more detailed, and level 3 is basically done by finite element analysis. So in each chapter or each part of API 579, there are 3 levels where assessment of a defect can be done.
Next question is from Mr. Albin Anto.
Question I can read, why is allowable stress same for 25 years, 30 years, and 40 years? See, here stresses are not changing because stress is subject to pressure and like a temperature and the diameter. So it does not change. However, the number of cycles which correlate with the fatigue crack or fatigue failure, since those are changing, so the stress, allowable stress remains same. But if number of cycles will increase, then there would be reduction in allowable stress by that ratio as per as maybe 31.3 section 327. So this is a criteria where number of cycles are allowed and number of cycles increase, then allowable stress decrease, Otherwise, if number of cycles are not applicable, like stress limit of particular component remains same throughout the design life if there is no metal loss.
So next, Mr. Naveen Verma, we have given you the permission to unmute. Please unmute and ask your question.
Yes. Can you hear me?
Yes, yes.
Okay. So my question is about how do you perform the fitness for service assessment for a piping system which is subjected to the random vibrations?
See, like here, what we presented is a real case, right? And this piping system is under cyclic service, and plant already completed like more than 35 years of service, right? So whether any life left for the fatigue life or not, that assessment is done. So Caesar 2 allows you to allocate number of cycles which could be sustained by the piping system, or you can also add the like a number of cycles. You can see the stress at that particular peak cycle load. So this is what the way is. This is what it is done. I hope it clarified your question.
Thank you, Naveen Verma. So we will move on to the next question. Yeah, Stimuli MD, we have given you the permission to talk. Please unmute your mic and speak.
So
Hello, I am
yeah.
yes, I am Stimuli. I'm dialing in from Papua New Guinea.
Yes, sir. Welcome, sir.
Thank you so much. I really appreciate the presentation that you presented. It was really insightful. Thank you so much for that. I have one question. How work in the mining industry, and we have pressure oxidation autoclaves. We have 4, and then I'm just trying to figure out how I can apply the fit for service assessment on those autoclaves to find how the remaining life, and
Yes,
the second thing is to adjust the inspection, testing, and preventive maintenance program that we have based on the current condition of the autoclave. Could you please shed some light on that, please?
So here, see, these kind of scenarios are there in the refining industry also. Like
Yep.
oxidation is a high temperature service. If it is a high temperature
Yes.
service, then there is a part, I think part 9 or 11, which cover the creep service, high temperature creep service assessment, right? And
Okay.
if I can go back to my slide, just a minute, I can show you.
Okay.
Just a minute. See here, the creep service is under section part number 10, right, sir?
Okay. Okay. Yep.
In the creep range. So this part can be applied on your autoclave, and you can see that how much life is left, because creep would cause oxidation. So this chapter is available, and it also give you the complete detail what you need to follow. Okay, sir.
Okay. Thank you so much.
Thank you, sir.
Thank you, Mr. Stimuli.
So we can conclude the discussion now. So because already we taken a lot of time, and people will be getting bored. Thank you very much, sir, who participated in this webinar. And we look forward to meeting you our next webinar soon as per our schedule. Thanks for participation. If you have some additional question, you can send by email, and our team would love to answer you. Thank you. Bye-bye.